Hello everyone, welcome back to Electronics 1. Last class we developed a T and a pi model, and the pi model, the nature of it being a fairly simple two-port input and two-port output, allowed us to develop some input and output characteristics. And the output characteristic we developed, we eventually showed that we have to stay above 0.2 volts across the collector to emitter, but beyond that we get a nice flat relationship where the collector current is completely independent of the collector to emitter voltage. What we're going to look at today is the early effect, which shows that that's not in fact quite the case. There is some dependence on the collector to emitter voltage and the collector current. Oops. Okay, let's start this discussion with a simple, let's set up a simple circuit where we have a fixed bias applied to the base that's fixing our base to emitter voltage. So let's put a bias on the base, and let's just call it VBE. That's what it is, and let's assume that this is 0.7 volts. Okay, so this is a fixed value that's keeping that base to emitter, right? This base to emitter junction held at 0.7 volts. Okay, but let's take the collector and let's connect it to a variable source that allows us to control the voltage across the collector to emitter. Okay, and let's assume that it can vary from the range of 0 to 10 volts. Okay, so this is a variable source here. Okay, so as a result of this bias on the input, we're going to fix our base current, but VC is allowed to change. Okay, so let's just say biased with fixed PPE to give a fixed IB. Okay, I guess I'll just label IB on here, but VCE is allowed to change, right, as we see here. Okay, and we know that when this collector to emitter voltage, let's say when it's 0, what's going to house the BJT going to operate? Well, that's below our saturation voltage, so the device, it's below VCE sat, so the device is going to be in saturation. And this is because our base to collector diode is forward biased. And let's just represent that base to collector junction on here on the diagram. Okay, and we know that as VCE approaches VCE sat, is about 0.2 volts, that the device will enter forward active mode. And let's just say approximately here. So this is just kind of the boundary. So this device is in forward active region, and this is because this base to collector diode becomes reverse bias. Okay, but what happens if we keep increasing the voltage from collector to emitter? Okay, so as VCE increases further, well, based on our diagram from last day, it suggested that that has no impact, that the current, the collector current, remains constant. But if we think about this a little more deeply, that base to collector junction is going to become more and more reverse biased. And your first thought might be, well, who cares? More, I'm going to say more and more reverse biased. And again, your first thought might be, who cares? It's still in forward active mode, and that's true. But what are the implications of this increasing reverse bias? So let's, for example, say VCE is at 5 volts for our circuit given above. The base to collector junction is going to be at minus 4.3 volts, right? We have, and again, we're talking, this is VCE. We know that the drop here is 0.7 volts, so we can, subtracting off that 0.7 volts, we can find the voltage across this junction. Okay, so we're at minus 4.3. And if VCE increases to 10 volts, then the base to collector junction is even further reverse biased, and now at 9.3 volts. And again, here, this is all assuming that PBE is equal to 0.7 volts. Let's dig into the physics of the junctions. Okay, so we look at down kind of at the depletion layer level here again, we have this base to emitter junction. We have this base to collector junction, right? So here's our emitter, here's our base, here's our collector, and this base to emitter junction, it's going to be at a fixed width because the bias across that junction is fixed at 0.7 volts, right? So we have a voltage across this junction of 0.7 volts, and therefore we have a fixed width. However, our base to collector junction, we recall some time ago we talked about the width being impacted by the magnitude of the bias, right? And increasing reverse bias is going to cause a widening of the depletion region. So when my base to collector reverse bias is minus 4.3 volts, I may have this width, and when I get to 9.3 volts, well, I'm going to be wider. Okay, so this width, for example, represents the width of the depletion region, the base to collector depletion region, when I have a reverse bias of 9.3 volts. What is important to note here is this effective base width. Okay, so remember we talked about effective base width here. So I'm going to extend this line. This line's not going to change. This edge of the base, the edge near the emitter, but this edge is moving, right? We have different base widths depending on our reverse bias. So we have an effective base width here that corresponds to a reverse bias of 9.3 volts, and we have another effective base width that corresponds to maybe I'll show this here. We have a wider base width that corresponds to a reverse bias of minus 4.3 volts. Okay, so now we see that this changing of the reverse bias is going to have an impact on the effective base width of the BJT. So as I'm just going to say the absolute value of the base to collector voltage increases, so the effective base width decreases. And this is known as the early effect. And you might wonder what the origins of the name is, where the word early comes from. Well, the this behavior was discovered by James Early and was therefore named after James Early. This effect is also referred to as base width modulation. Okay, but why should we care? Well, you'll recall that back a few lectures ago that we, through some derivations, discovered that the collector current was equal to saturation current times E to the base to emitter voltage divided by the thermal voltage. But you'll also recall that the saturation current was inversely related to the base width. In fact, the saturation current was equal to, as a function of our cross-sectional area or fundamental unit of charge, our diffusion constant for electrons, our intrinsic concentration squared, our doping concentration, but here's the important one, and inversely proportional to our effective base width. So, all of that to say, if the effective base width decreases, as it does with increased reverse bias, then our collector current increases. Okay, so what does our characteristic, our IV characteristic of our output look like when we take this into account? Okay, so let's plot it again. So the collector current as a function of VCE, and let's put our VCE sat point on here. And again, last day we come up with a characteristic that looked like this. Looked like the collector current was completely unrelated to our collector to emitter voltage. Right? So, however, this this is a simplified model. So this flat characteristic is a simplified model of the output behavior, when in fact the true output behavior, as we just concluded, with increasing reverse bias, that's a function of our collector to emitter voltage, we'll get increasing collector current. Okay. And I'll remind you again that this this curve is a function of beta times our bias current, or in fact it's our collector current at a specific bias. But again, we see that now the effect is such that this current increases with increases in collector to emitter voltage, with increases in reverse bias. If we take and we extend this, the slope of this characteristic back to where it intersects our voltage axis, this point is known as the early voltage. And this is a characteristic that you'll find specified in the datasheet for a bipolar junction transistor. So it'll give you a sense of the impact of base width modulation, or impact of increasing reverse bias or increasing collector to emitter voltage on the output. Okay, so if we for a second here ignore the small saturation voltage, which is VCE sat, then the increase in collector current can be approximated as follows. Right? Note that the response here is a flat line of a constant slope. So if we look at the change in that collector current, the change in collector current is going to be equal to the slope times the collector to emitter voltage. That slope can be found as the collector current, the DC, the collector current due to the DC bias. So basically we're ignoring this saturation voltage and taking this collector current due to our bias, extending that to our point where we intersect the axis, which is our early voltage, and that gives us our slope of our characteristic. That slope times the collector to emitter voltage will give us our change in collector current as a function of our collector to emitter voltage. And looking at, if we look at a plot pulled from Cedar Smith here, figure 6.18, we notice that for increasing levels of bias point or of increasing input drive, right? So this is for increasing IB, that the slope of the characteristic changes. But in every case, the slope is a function of this early voltage and the collector current at that specific operating point, right? So maybe this is collector current 1 versus collector current 2, and so on. Okay, so if that change in collector current is given by this, then our total collector current is our collector current due to our input bias plus the collector current due to the early effect. Okay, so our collector current is therefore the collector current due to our bias, due to our input. So this we might call IC. This is the DC operating point, or the large signal component of our collector current, but that large signal component is also impacted by the early effect, which we said was the operating point divided by our early voltage times my collector to emitter voltage. All right, just rearranging this to collect terms, or factoring out the IC, I guess. I can get an expression that you will most often see as this plus VCE over my early voltage. Okay, how do we account for this early effect in our models? Because our pi and t model to date suggested that there was no impact on the output behavior in response to changes in the voltage across the output. Okay, so to produce a slightly improved model, or an improved model to take account for this early effect, we can add a component to our model. And that is to make the collector current source non-ideal. So an ideal current source, as was depicted in our earlier T and pi models, was one that had an infinite output resistance. But now we're going to make them non-ideal, or have, or in other words, have a finite output resistance, something less than infinity. So the pi model becomes so our original model, but now we add a finite output resistance to this model. Like this. Okay, and that output resistance is calculated as the early voltage divided by the collector current at our operating point. Okay, we can do the same modification to the T model to develop an improved T model. And so taking our original T model that looked like this, and again we're adding a output resistance across the collector to emitter. And this adds a particularly in the T model, introduces a particularly specifically more challenging model to solve for in a circuit, and often we will therefore ignore the output resistance just to make for a simplified analysis of our circuit, albeit a bit less accurate. Okay, so there's our the early effect, and or also referred to as base width modulation. And here we have a improved version of our pi and T models that account for the early effect that is caused by increasing collector to emitter voltages on the output.